Okay guys, I'm going to also make a little video for section 8.7 in which we are dealing with imaginary numbers for the first time. And first of all, let's look at a definition of an imaginary unit. Two things to keep in mind, okay? So the square root of -1 is defined by the lowercase letter I, okay? Just keep that in mind, okay? The square root of -1 equals a lowercase I. Conversely, I squared is equal to -1. Okay, both of these things are going to be important to us as we deal with imaginary numbers. So let's look at one. Let's say that I had the square root of -9. Now, in the past, right, you've been told there is no real number square root for this. There isn't. Okay, but there is an imaginary number root for it. And the way we're going to do that is to break this thing. Remember, let's go back just a little bit. If I have the square root or any root of a times b, it's the same thing as the square root of a times the square root of b. So we're going to use this to help us out here. So I'm going to split this up into the square root of 9 times the square root of -1. Okay. Well, obviously the square root of 9 is simply 3. And what's the square root of -1? Well, the square root of -1 is defined as a lowercase I. So the square root of -9 is 3i. Okay, that's how we would work that. Let's take another one. Let's say that I had the square root of -18. Okay, once again, I'm going to split this up. So the square root of 18, I'm going to get rid of that negative. Now, if we had an odd numbered root, this doesn't apply, okay? So that times the square root of -1, because if I multiply these together, I get -18. All right, well, this isn't, 18 of course is not a perfect square, but maybe there's a perfect square within there. And certainly if I think about it, 18 is 9 times 2, and 9 is a perfect square. Okay, so let's go ahead and look at this process. So when I do this, then the square root of 9 is 3. That would come out, leaving me 3 times the square root of 2, and the square root of -1 is defined as I. So here's what I have. 3 times the square root of 2 times I. Now how do I structure that solution? Well, I'm going to move the I so that it's here with the coefficient, or it's right in front of the radical sign. So I would show this as 3i square root of 2. That would be the proper way to write that. So the square root of -18 is 3i times the square root of 2. Okay? Let's look at another definition. Let's look at the definition of a complex number. So, a complex number is any number that can be described in this way. Okay? It has a real number component and it has an imaginary number component. Let's take a look at an example. I could have 2 plus 3i. Okay, that's a complex number. This is a real number, and here's an imaginary number. Okay, I could conversely look at 4 minus 7i. Okay, there's another complex number. It has a real number component, and it has an imaginary number component. And they can certainly be more complex than that. But overall, if there's a real number part and an imaginary number part, you're talking about a complex number. Well, let's look at how we do arithmetic on complex numbers then. So we'll start with addition. Okay, so let's take a look at adding complex numbers. So let's say that I had 3i -3 minus 5i, and I'm adding that to 4 minus 6i. Okay, so I am adding these two complex numbers. Well, let's simplify it by getting rid of the parentheses first. So this is just going to be -3 minus 5i plus 4 minus 6i. And now I'm going to combine like terms. I've got constants here, and these are like terms. Okay, they're both imaginary numbers that are raised to the same exponent in this case. Okay, so these are like terms. -3 plus 4 is 1. -5i minus 6i, -11i. Okay, so there would be the sum of these two complex numbers. Well, let's look at it if it's subtraction. It's going to be the same thing, but this will help me point out something that oftentimes can mess us up. So let's say that I have 4 minus 7i, and I am going to subtract negative 3 plus 2i. Okay, so there's two complex numbers, and I'm doing subtraction between them. Once again, let's get rid of the parentheses. Okay, so let's simplify this. So I'd have 4 minus 7i minus a negative 3 would be positive 3, minus a positive 2i would be negative 2i. So remember, if you're subtracting, if you're going to get rid of the parentheses, it's going to change the signs of every term that's inside the parentheses. You're distributing the negative 1. All right? So I have 4 plus 3, which is 7, negative 7i minus 2i, and that would be negative 9i. And again, I'm going to put the real number component in front of the imaginary number component when I write a complex number. Okay, so that's all there is to adding and subtracting it. Well, how about multiplication? Let's take a look at what happens when we multiply complex numbers. So let's say that I have this imaginary number and I am multiplying it to this complex number, right? I'm going to multiply this term to that and this term to that both. Okay, so I'm going to have 5 times 4, 20i minus 35i times I squared. And remember, I squared is negative 1. I can substitute negative 1 for this. So here I have 20i still, there's nothing changes there, minus 35 times negative 1. Okay, so when I multiply negative 35 and negative 1, I get positive 35. I'm going to move that to the front because it's a real number. Okay, and then I have positive 20i. Okay, so again, the real number component shows up first. But notice that I'm able to replace I squared with negative 1. All right, well, let's look at one that's a little bit more complex than that. I have this complex number, and I'm multiplying it to this complex number. So I'm going to have to FOIL this thing. All right. 8 times 2 is 16. 8 times I. Negative 3i times 2. Negative 6i. And I'm going to have negative 3i times I squared. These are like terms. Let's combine those. So I'm going to have 6i, and if I have 8i and I take 6 of them away, I'm left with 2i's. Okay. I have negative 3, and remember, I squared is the same thing as negative 1, so I'm going to substitute that in there. So 16 plus 2i, negative 3 times negative 1 is plus 3. Right. Now, so notice that it's not an imaginary term. It's a constant, so I need to add it to here. 16 plus 3, 19 plus 2i. Okay, so when I FOIL that, this is what that is going to simplify to. All right, let's look at another thing. Let's look at division. That was multiplication. Let's take a look at division. If I had 8 divided by 3i, so I've got something that's divided by an imaginary number. Okay, when I encounter this, what I want to do is I want to get the imaginary number out of the denominator. Okay, and one way I can do this is to multiply both by I. Because think about it, when I do that up here, 8 times I, there it is, but down here I have 3i times I. Okay, this is going to be I squared. So again, no change up top, but I squared is equal to negative 1. So I'd have 3 times negative 1. So this is going to end up being negative 8i over 3. You could show it likewise as negative 8/3 I. Either one of those is perfectly fine, perfectly legitimate. Okay. So what I want to do again is get the imaginary part out of the denominator. And yes, you could have multiplied it by 3i in both cases, but okay, but just multiplying it by I is going to get rid of it, because I squared, I can replace I squared with negative 1. Okay, well, let's look at one. It's a little bit more complex than that. So, and this is about as complex as it's going to get for you at this point. So let's say that I have this complex number divided by this complex number. Okay, so here's what you do in this case. I'm going to multiply by the conjugate. Okay, remember the conjugate is the same two terms except the sign is different. So since it's negative here, the conjugate would be positive. Okay, I'm going to multiply the top by the same thing. All right, let's look at what happens when I do that. I'll let you foil that, okay, and deal with the numerator on your own. But because the important point here is, why do I multiply by the conjugate? What does that do? Again, we're trying to get imaginary numbers out of the denominator. So when I do that, let's take a look. So I'm foiling these things. 4 times 4 is 16. Okay, I have plus 20i minus 20i minus 25i squared. Okay, so anytime we multiply something by the conjugate, these middle terms cancel out. They drop out. Okay, so again, I'll let you deal with whatever's up there. So that's 0, but look what I have. 16 minus 25i squared. And I squared is negative 1. Okay, so let me replace that. So I have 16 minus 25 times negative 1. So I'd have 16 plus 25. So again, I started out with this complex number. If I multiply by the conjugate, then my numerator is going to become a real number. It's going to become a constant, in this case 41. And you could deal with everything that's in the numerator. Okay, so there's that. All right, let's look at raising an imaginary number to powers. Okay, so this will be the last thing associated with this. All right, so if I have I to the first power, that's just simply I. If I have I squared is negative 1. If I had I raised to the third power, I have negative I. If I have I to the fourth power, that is positive 1. And this same pattern is going to follow from there on. So I to the fifth is going to be equal to I to the sixth is going to be equal to negative 1. I to the seventh is going to be equal to negative I. And I to the eighth is going to be equal to positive 1. And it would continue on from there. Okay, so I to the ninth, I to the 10th, I to the 11th, I to the 12th. You could extrapolate that on and on and on. Okay, well, what does that mean? If we're knowing that this is the case, and I'm gonna just kind of, well, okay, we'll leave it right there. Knowing that that's the case, as a matter of fact, let's put these in different colors. So okay, that would be I. This is negative 1. Negative I, and this would be positive 1. Okay, so knowing that, we can use that to simplify. We can use that to simplify imaginary numbers that have been raised to power. So for instance, if I had I raised to the 25th power, okay, I'm going to look for something, or how I can break this up so that I can give it a numeric value somehow. Okay, so you kind of got to play around with it. If I took it and you're using rules of exponents, so I'm going to just break this into this and this, right? I to the 20 raised to the 24 times I raised to the 1 would be equivalent to that. And let me break this up into something that's going to give me a number. Okay, so if I had I to the 4th raised to the 6th power, I to the 4th raised to the 6th power, same thing as I to the 24th. Okay, and there's that. But I to the 4th is 1. So I can put that value in. 1 raised to the 6th power times I. So I can simplify I to the 25th power as 1 I, or just, in this case, just I. It would simplify to that. Or you could just extrapolate this table on out as well. Okay, you could do that also. Okay. If I had, let's just kind of do one more. If I had I to the negative 14th. Okay, rules of exponent. I'd put that down there in the denominator, and I'm looking for a value that will give me a number. Okay, and so, well, it needs to be even. So I'm looking for something that's why I picked 4 here. And that's why we took the 1 out here, so we could deal with an even number power or even numbered exponent. So either I squared or I to the 4th. So if I looked at this, okay, well, 1 over, if I had I squared raised to the 7th power, okay, that's I to the 14th. Okay, that's what that is. But I squared it has a numeric value to it. Okay, so if I do that, I would have 1 over negative 1 to the 7th power. Negative 1 to the 7th power is going to be negative 1. Okay, so this would simplify down to negative 1. Okay, so you got just a few problems like this at the end of the homework assignment. You can play with them, and hopefully you'll have an epiphany associated with it. So you want to make sure that you're dealing with, so here, split it so that you've got something that's an even number, and then you want to pick, so I to the 2nd, I to the 4th, I to the 6th, I to the 10th, I to the 8th, I to the 12th, something that's going to give you a numeric value that you can substitute in, and you're just going to play with rules of exponents in order to do that. All right, so hopefully that'll help you with 8.7, and likewise get that one done. All right.